When dealing with motor branch circuit calculations according to NEC section 220.2b, you are permitted to drop the fractional part of an ampere. In your specific example, if the calculation results in 30.25 amps, you can disregard the 0.25 amps. Therefore, a number 10 wire would be acceptable, assuming it meets all other requirements such as ampacity and overcurrent protection. Now, regarding oven calculations, NEC section 220.2b does not allow for rounding down or dropping small percentages of kilowatts. The full kilowatt rating of the oven must be used in your calculations without any reductions or rounding. To summarize, you are correct in your understanding of 220.2b for motor branch circuit calculations where fractional amperes can be dropped, but it's incorrect to apply this rule to oven calculations where the full kilowatt rating must be used. When performing electrical calculations, it's essential to understand the specific rules and how they apply to different types of loads. Motors and ovens are treated differently under the code due to their varying characteristics and impact on the electrical system. Always refer to the latest edition of the National Electrical Code for the most accurate and up-to-date information. Let's delve a bit deeper into why these calculations are performed and the reasoning behind the code rules. Motor branch circuit calculations are crucial for ensuring that the wiring supplying a motor is adequately sized to handle the motor's full load current, starting current, and any other applicable factors. The code requires that the conductors have sufficient ampacity to prevent overheating and potential fire hazards. The allowance to drop fractional amperes in motor calculations acknowledges that small rounding differences have a negligible impact on the overall safety and performance of the circuit. In contrast, oven calculations are critical for determining the total load on a service or feeder, and the code aims to ensure that the electrical system can handle the combined load of all appliances and equipment. Ovens, particularly commercial ovens, can draw significant amounts of power, and any rounding down of their kilowatt rating could lead to an underestimation of the total load. This could result in an undersized service or feeder, which could overload the electrical system and cause breakers to trip or, in more severe cases, pose a fire hazard. Furthermore, it's important to consider the specific types of conductors being used in the motor branch circuit. In your question, you mentioned TW wire, which is an older type of insulation with a low temperature rating compared to more modern insulations like THHN or THWN. The ampacity of a conductor is directly related to its temperature rating, so it's essential to select the appropriate wire size based on the conductor's insulation type and the ambient temperature. Using a conductor with a lower temperature rating may require a larger wire size to achieve the required ampacity. Also, remember that the NEC contains tables that specify the allowable ampacities of different conductors based on their size, insulation type, and temperature rating. These tables are essential tools for performing accurate motor branch circuit and oven calculations. In addition to the conductor size, it's also crucial to select the appropriate overcurrent protection device, such as a circuit breaker or fuse, for the motor branch circuit. The overcurrent protection device is designed to protect the circuit from overloads and short circuits, and its size must be coordinated with the ampacity of the conductors. The NEC contains specific rules for sizing overcurrent protection devices for motor circuits, taking into account the motor's full load current, starting current, and other factors. Let's talk more about overcurrent protection. Selecting the correct overcurrent protection for a motor circuit is essential to protect the motor and the branch circuit conductors from damage due to overloads and short circuits. The NEC provides detailed guidelines for determining the appropriate size of the overcurrent protection device, which may be a circuit breaker or fuses. The general rule is that the overcurrent protection device should be sized no larger than the conductor's ampacity, but there are exceptions for motor circuits to accommodate the motor's inrush current during starting. The inrush current, also known as the locked rotor current, can be several times higher than the motor's full load current, and a standard overcurrent protection device size strictly according to the conductor's ampacity would likely trip during motor starting. To address this, the NEC allows for the use of time delay fuses or inverse time circuit breakers, which can withstand the high inrush current for a short period without tripping. The specific rules for sizing the overcurrent protection device for motor circuits depend on the motor's full load current, service factor, and temperature rise, as well as the type of overcurrent protection device being used. It's crucial to consult the NEC and follow the manufacturer's instructions when selecting and installing overcurrent protection devices for motor circuits. Now let's shift our focus back to oven calculations and explore some additional considerations. As previously mentioned, the NEC requires that the full kilowatt rating of the oven be used in the calculation without any rounding down. This is because ovens, especially commercial ovens, can draw significant amounts of power, and any underestimation of their load could have serious consequences. In addition to the kilowatt rating, it's also important to consider the oven's duty cycle, which refers to the percentage of time that the oven is actually in use. Some ovens may have a relatively low duty cycle, while others may be in continuous operation for extended periods. The duty cycle can affect the overall load in the electrical system, and it may be necessary to adjust the calculations accordingly. The NEC provides guidelines for calculating the demand factor for ovens, which takes into account the duty cycle and other factors. The demand factor is a percentage that is applied to the oven's kilowatt rating to determine the actual load that the oven is expected to draw. Another important consideration for oven calculations is the type of oven being used. There are many different types of ovens, including electric ovens, gas ovens, and microwave ovens, and each type has its own unique electrical characteristics. Electric ovens typically have a higher kilowatt rating than gas ovens, and they require a dedicated branch circuit. Microwave ovens, on the other hand, have a relatively low kilowatt rating and can often be plugged into a standard 120 volts receptacle. The type of oven being used will affect the calculations and the wiring requirements. When performing oven calculations, it's also important to consider the voltage of the electrical system. Most ovens are designed to operate at either 208 volts or 240 volts, and the calculations must be based on the correct voltage. If the voltage is not known, it's essential to measure it before performing the calculations. Using the wrong voltage in the calculations can lead to inaccurate results and potentially dangerous situations. Furthermore, the NEC requires that the ovens be installed in accordance with the manufacturer's instructions. This includes following the manufacturer's recommendations for wiring, grounding, and overcurrent protection. Failure to follow the manufacturer's instructions can void the oven's warranty and may also violate the NEC. In summary, motor branch circuit calculations and oven calculations are essential for ensuring the safety and reliability of electrical systems. Understanding the specific rules and how they apply to different types of loads is crucial for performing accurate calculations and selecting the appropriate wiring and overcurrent protection devices. Always consult the latest edition of the National Electrical Code and follow the manufacturer's instructions when performing these calculations. Remember, electrical work can be dangerous, and it's always best to consult with a qualified electrician if you have any questions or concerns. Okay, let's dig even deeper into specific scenarios you might encounter when dealing with motor and oven circuits, providing practical guidance for each. Firstly, let's imagine you are wiring a three-phase motor for an HVAC system. The motor nameplate indicates a full load current of 25 amps. You're using THHN conductors in a conduit, and the ambient temperature is within the standard range. To determine the minimum conductor size, you typically refer to NEC Table 310.15. B16. This table provides ampacities for various conductor sizes and insulation types. For a 25 amps motor, you might initially think number 12 AWG THHN is sufficient, as it's often rated for around 30 amps. However, NEC 430, specifically Article 430.22, requires that motor circuit conductors have an ampacity of not less than 125% of the motor's full load current. Therefore, you'd calculate 25 amps times 1.25, which equals 31.25 amps. Now applying 220.2 B, you can drop the 0.25, resulting in 31 amps. Looking back at table 310.15, B16, number 10 AWG/THHN is rated for 35 amps, making it the appropriate choice. Secondly, consider the overcurrent protection. Article 430 dictates how to protect motor circuits, differing from standard branch circuits. The overcurrent device must protect against short circuits and ground faults, but also allow for the motor's inrush current during startup. You can't simply use a breaker or fuse sized at 125% of the full load current, as that would likely trip during startup. Instead, you might use a dual element time delay fuse or an inverse time circuit breaker. These devices allow for a temporary overload, such as the inrush current, without tripping. For our 25 amps motor, you might start by looking at a breaker or fuse sized at 175% to 250% of the full load current, depending on the motor's design letter and the specific type of overcurrent device. Consult NEC Table 430.52 to determine the maximum allowable overcurrent protection. Thirdly, let's move on to oven calculations. Suppose you are installing a commercial electric oven with a nameplate rating of 15 kilowatts at 208 volts. The first step is to convert kilowatts to amps. Use the formula amps equals kilowatts times 1000 divided by volts times the square root of 3 for a three-phase system, or volts for a single-phase system. Assuming it's a three-phase oven, the calculation would be 15 kilowatts times 1000 divided by 208 volts times 1.732, which equals approximately 41.6 amps. Here's where it's crucial to remember that you cannot drop any fractional part of the kilowatt rating. The NEC requires you to use the full 15 kilowatts in your calculations. Therefore, you'll need to select conductors with an ampacity of at least 41.6 amps. Referring back to NEC Table 310.15. B16, you'd likely need number 8 AWG/THHN, which is typically rated for 50 amps. This ensures the conductors can handle the oven's full load. Fourthly, the overcurrent protection for the oven circuit is more straightforward than for motor circuits. You'll typically select a breaker or fuse with an amperage rating close to the conductor's ampacity. In this case, a 50 amps breaker would be a suitable choice. The NEC also requires that the overcurrent protection device be sized no larger than the conductor's ampacity, as stated in Article 240. In commercial kitchens, it's common to have multiple ovens. To calculate the total load for the service or feeder supplying these ovens, you can't simply add up the nameplate ratings of all the ovens. The NEC allows for demand factors to be applied, recognizing that not all ovens will be operating at their full capacity simultaneously. The demand factors are typically found in NEC Table 220.55. For example, if you have 3 identical 15 kilowatts ovens, the total connected load would be 45 kilowatts. However, the demand factor might be 80%, reducing the calculated load to 36 kilowatts. This reduced load is what you'd use to size the service or feeder conductors and overcurrent protection. Fifthly, it's important to consider voltage drop. Voltage drop occurs when the voltage at the load is lower than the voltage at the source due to the resistance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To calculate voltage drop, you'll need to know the conductor length, the conductor size, the load current, and the voltage of the circuit. There are various online calculators and software programs that can assist with voltage drop calculations. If the calculated voltage drop exceeds the recommended limits, you'll need to increase the conductor size to reduce the resistance and minimize the voltage drop. Sixthly, always pay attention to ambient temperature correction. The ampacity ratings in NEC Table 310.15. B16 are based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher, the conductor's ampacity must be derated to account for the increased heat. The NEC provides correction factors for different temperature ratings and ambient temperatures. For example, If the ambient temperature is 40 degrees Celsius and you're using THHN conductors with a 90 degrees Celsius rating, you'll need to multiply the ampacity by a correction factor of 0.91. This rating ensures that the conductors don't overheat and cause a fire hazard. Seventhly, grounding is critical for both motor and oven circuits. Proper grounding provides a path for fault current to flow back to the source, tripping the overcurrent protection device and preventing electrical shock hazards. The NEC requires that all metal enclosures, such as motor frames and oven housings, be grounded. This is typically accomplished by connecting a grounding conductor from the equipment to the grounding bus in the electrical panel. The size of the grounding conductor must be based on the size of the circuit conductors, as specified in NEC Table 250.122. Eighthly, remember to consider the effects of harmonics. Harmonics are distortions in the electrical waveform that can be caused by nonlinear loads, such as variable frequency drives used with motors and some types of electronic ovens. Harmonics can cause overheating of conductors, transformers, and other electrical equipment. If you suspect that harmonics may be present, it's important to conduct a power quality study and take steps to mitigate the effects of harmonics, such as installing harmonic filters. Ninthly, it is essential to consider the working space around electrical equipment. The NEC requires that there be adequate working space around electrical equipment, such as motor starters and oven disconnects, to allow for safe operation and maintenance. The working space must be clear of obstructions and must be large enough to allow personnel to safely access the equipment. The specific requirements for working space are found in NEC Article 110. Tenthly and finally, be sure to document your calculations. Keeping a record of your calculations, including the conductor size, overcurrent protection device rating, voltage drop calculations, and any other relevant information can be helpful for future reference and for troubleshooting purposes. It can also be required by local electrical inspectors. Always refer to the latest edition of the National Electrical Code for the most accurate and up-to-date information, and consult with a qualified electrician if you have any questions or concerns. Electrical work can be dangerous, and it's important to take all necessary precautions to ensure your safety and the safety of others.